All right, so we're constantly hearing about AI that can write, talk, and create amazing things. But how does it actually understand context? How does it remember what was said at the beginning of a sentence by the time it gets to the end? Well, today we're going to dive into exactly that, the architecture that first gave AI a real memory.
So, to really get why this was such a huge deal, you first have to understand the problem they were trying to solve. And this quote, it just nails it. Basic neural networks, the early ones, are a lot like the main character in the movie Memento. They've got a serious short term memory problem. Every single moment, every piece of data is brand new to them. They have no memory of what just happened. And you can probably guess why that's a massive problem, right? For so many things we want AI to do, like understanding language or even predicting stock prices, the order of events, that context, is absolutely everything. Okay, look at this. On the left, you've got your standard memoryless network. It sees the word apple. What does it do? It's totally lost. Is that a fruit? A tech company? It has no clue, because it treats every word like a brand new isolated event. But now, look to the right. This is a sequence model, a network with memory. It sees the words I ate Anne before it sees apple, and boom, it instantly knows we're talking about the fruit. That ability to connect the dots in a sequence, that's the whole game right there. So faced with this amnesia problem, what was the first big idea? How did engineers try to fix it? Well, the first solution was actually pretty elegant and kind of simple. They just gave the network a loop. And that simple idea, that loop, gave us this, the recurrent neural network, or RNN. The real magic here is that feedback loop. See, as the network processes an input, it doesn't just produce an output. It also passes a little piece of information, kind of like a summary of what it just saw, back to itself for the next step. We call this summary the hidden state, and you can think of it as the network's very own short-term memory. Now, the best way to really wrap your head around this loop is to unroll it in time, just like you see here. Imagine each of these links is one word in a sentence. The network chews on the first word and creates that memory, that hidden state. Then it passes that memory, plus the next word, into the next step. And so on and so on. It creates this awesome chain reaction where the meaning of each new word is shaped by everything that came before it. So, this was a huge first step, right? A brilliant idea. But there was a fatal flaw. The RNN could remember, yeah, but its memory was leaky. It would fade away, and honestly, it would fade away surprisingly fast. The culprit here is a really tricky problem in deep learning called the vanishing gradient. Think of it like this. To learn, the network has to send a correction signal backwards, from the end of the sentence to the beginning. It's like whispering a secret back down a long line of people. But in a basic RNN, with each step back, that whisper gets quieter and quieter and quieter. It shrinks exponentially. So as you can see on this chart, a really strong, clear signal at the end becomes a faint, useless whisper by the time it gets to the start. The beginning of the network never really learns from the end result. So what's the bottom line here? In practice, this means a standard RNN really only remembers the last maybe 5 to 10 words. That's it. Anything that happened before that is basically gone, completely forgotten by the time the network tries to learn. And if you're trying to understand a whole paragraph, or even just a long, complicated sentence, that's just not going to cut it. Okay, so to fix this whole fading memory disaster, researchers back in the late 90s came up with something way more complex. But, wow, was it powerful. They called it the Long Short-Term Memory Network, or for short, the LSTM. The absolute genius of the LSTM, the secret sauce, is that it adds a whole second channel for information. So it still has that short-term memory we talked about, the hidden state. But now it also has this thing called the cell state. And the best way to think about this is like an express conveyor belt for memory. It just runs straight down the entire chain, making it super easy for important information to travel a long, long way without getting lost or fading out. But here's where it gets really clever. This memory conveyor belt isn't just a passive thing. It's actively managed by these things called gates. Think of them as little intelligent gatekeepers. They're actually tiny neural networks inside the main network, and their whole job is to learn what to do with the information on that belt. They decide what old stuff to throw away, what new stuff is important enough to store, and what part of that memory is useful right now. All right, so let's meet these three gatekeepers. Understanding what each of them does is the real key to seeing how an LSTM can think and remember things over these really long stretches of time. First up, we have the forget gate. Its job is exactly what it sounds like. It decides what information to throw away.
So if a sentence was talking about samosas and then suddenly switches to pasta, the forget gate learns to go, okay, new topic, we don't need the old subject anymore, out it goes. It's basically cleaning house.
Okay, next is the input gate. This gate does the opposite. It decides what new information is important enough to actually add to that memory conveyor belt. So when it sees a new, important word like samosa or cheese, it learns to recognize that as key context and says, yep, this is important, we're going to store this for the long term.
And last but not least, we have the output gate. This one looks at everything on the memory belt and decides what specific piece of it is useful for the task at hand right now. So if it needs to predict a type of cuisine, it can look at its memory, see pasta and cheese sitting there on the belt, and the output gate will say, okay, let's use that information to make our prediction, Italian. So when you put them all together, these three gates create this incredibly sophisticated system for managing memory. And this whole architecture, it wasn't just some cool academic theory. It very quickly became the engine driving a ton of the tech we now use every single day. And, the impact was absolutely massive. Before Transformers came along around 2017, LSTMs were the undisputed kings of the hill for anything involving sequences. We're talking pretty much all the state-of-the-art results in things like machine translation, speech recognition, and text generation. They were all powered by LSTMs. They completely changed the game for everything from Google Translate to the autocomplete on your phone. It's a pretty remarkable story. The LSTM was actually thought up way, way back in 1997. But the computers back then just couldn't handle it. It was too complex. It wasn't until around 2015, when our hardware finally caught up, that they had their moment. Some people even call it the year of dominance. And yeah, newer things like the transformer architecture have taken the spotlight for a lot of big tasks now, but we can't forget that the LSTM was that crucial, game-changing step that finally taught AI how to really understand sequences. So by giving AI this really elegant system of gates to manage its own memory, we unlocked abilities that honestly felt like science fiction not too long ago. Which leaves us with a really fascinating final thought, one that kind of mirrors the architecture we just talked about. We've gotten really good at teaching AI how to remember, but maybe the bigger, more important challenge moving forward is teaching it what it should be allowed to forget.